Hey, what's up everybody? This is the Helpful Hacker, and today we are going over the Cryptography Basics room from TryHackMe. So we'll jump right in and get started with task number 1, the introduction. So read through all this. It's just going to talk about, how we all use encryption all the time and how it's super important. It's fundamental to how computers, networking, application security, browser security, it all involves cryptography, whether or not you know it. And so it's really important. And then they let you know that this is the first of 3 rooms, so we will get deeper into cryptography if you go through all of the rooms. And just kind of big picture to help people out, the idea behind cryptography, or what cryptography is it is the converting of information. So you have a piece of information and you want to convert it into an unreadable format. Now, how do we do that? We use algorithms and keys and stuff like that, and don't worry too much about that yet. We'll talk about that in later tasks, but for now, just keep in mind, what's the goal behind cryptography? It's to be able to take a piece of information and convert it into an unreadable format. And then also kind of the goal of cryptography is, when required, we should be able to turn it back into a readable format. So that's what we're talking about when we're talking about cryptography. So make sure you read through everything. Inside this room, we're going to be learning the basic cryptography terms. We're going to talk about how important it is, and then we'll learn some different types of ciphers, and we'll learn what a cipher is. And then we'll go over some basic math that is commonly used in cryptography. And when I say basic, if you don't have a math background, you should be able to get the general idea, but don't stress too much, because chances are, as long as you have a good idea of how it works, that's enough for now, and you can learn more as you continue through these rooms to delve into cryptography. So let's mark complete. Make sure you've read everything. And with that, we are done with task number 1. Now it's on to task number 2, the importance of cryptography. So basically, read through all this. I mean, they do a pretty good job here, so I'm not going to explain too much, but they just talk about how cryptography is used pretty much everywhere, and it's super important because if we didn't have it, information would just be stolen constantly, and very private and important information, like, health records, credit card numbers, social security numbers, things like that. And so cryptography is used a lot, even if you don't, you might not see it on the front end, but a lot of it's happening. So make sure you read through all this. They'll give you some examples of even just getting on to TryHackMe, how cryptography is used. And then let's see, the other thing that they do bring up is PCI DSS, which is for credit card compliance. So that's in this paragraph right here. Make sure you read that. And then they also talk about a few other laws and regulations regarding like privacy and stuff. And a big part of those laws and regulations is that it's required that sensitive information be encrypted. That's a big part of those laws. So whether or not you like it, like, cryptography is used on, or it should be used on, all of your sensitive data that you put into any website. So you put in a credit card number, social security, or you access your lab results online, that all needs to be encrypted in order for these companies to actually be following the laws and regulations. So make sure you read through all this, and then we'll jump down to the question: what is the standard required for handling credit card information? So that is PCI DSS. And yeah, I can't remember exactly what that stands for. It stands for like payment card industry data something. I'm sure it says somewhere in here. Payment card industry data security standard. But yeah, so that's the standard for using credit card information. So anytime you buy anything on the internet, that's happening. Okay, so mark that complete. And with that, we are done with task number 2. Now it's on to task number 3, plain text to ciphertext. Okay, this is really cool. and make sure you read through everything. I would read through everything first and just take a minute, look at the diagram, see if you can kind of understand it. But what will help is if we go through all the definitions and then you look back. Okay, so plain text, what is it? Plain text is just the original message or that piece of information, just written so anybody can understand it. Ciphertext is the result of encryption. So if you encrypt plain text, it becomes ciphertext. Okay, and ciphertext just means it's an unreadable version of the plain text. Now, a cipher is an algorithm, so a mathematical algorithm or method, and that is what actually converts, those are like the rules that are followed to convert the plain text into ciphertext and back again. So, and then they mention right here, ciphertext or a cipher is usually developed by mathematicians. So yeah, don't worry again if you're not great at math, you still should be able to understand pretty much all of this. And then we have keys. Keys are really important, and a lot of time we talk about keys in a very hypothetical, or not hypothetical, but when we talk about keys, we just see this nice little image of a key in all these diagrams. But I really want you to think of an actual string of bits, right? So it's like a string of information. And in this case, it could be like a string of bits or characters or whatever, depending on the cipher that you're using. And this key is used to actually encrypt and decrypt the data. Okay, so it says right here, in general, the used cipher is public knowledge. However, the key must remain a secret unless it is the public key in asymmetric encryption. They'll talk about that later. So this is where some people can kind of get confused. So the cipher is the algorithm, and the key is what we actually are is what the cipher uses. So we plug the key into the cipher to actually encrypt stuff or decrypt stuff. Okay, so hopefully that makes some sense. You can always reference back to these definitions. And I think it says that right here. Yeah. So the key is a string of bits the cipher uses to encrypt or decrypt data. And then we have encryption, which is converting plain text into ciphertext, so making just readable information into a non-readable format. And then decryption is taking the non-readable format and converting it back into a format that we can read. So pretty straightforward. So now let's go take a look at the actual diagrams that they have here, right? So they just give us a quick illustration. Make sure you read everything, but you have the sender of a message. So this person wants to send a message. And so they write out their message in plain text. That message then gets encrypted. They use a key and a cipher. Okay. So the cipher, everybody knows what the cipher is. Everybody knows how it works, but the key is the secret part. So you plug that key into the cipher, and then you use that to encrypt the plain text, and then it becomes ciphertext. Now, on the receiving end, let's say this person is trying to receive the message. They'll get the ciphertext. Now, what they have to do is decrypt that. So they will use the key, right, which is, again, is a secret. Nobody should know what the key is. And they will use the cipher along with the key and the ciphertext, all of those combined together, right? They plug in the ciphertext, they plug the key into the cipher, and they should be able to decrypt the ciphertext back into plain text. Okay, so hopefully those make some sense. Make sure you read through everything, and then let's jump down to the questions. What do you call the encrypted plain text? That would be ciphertext. And then what do you call the process that returns the plain text? That would be decryption. So those are the answers, and with that you are done with task number 3. Now it's on to task number 4, historical ciphers. So this is kind of cool information, and it helps kind of relay an idea, but I wouldn't say it's crazy important. So I'm not going to get too deep into this, but it is pretty cool. So cryptography's been around forever, since like super long ago. And the one that they always talk about is the Caesar cipher, which is super old. And basically all that cipher is you take the message, so TryHackMe, right? This is the plain text. And the key is the number 3. So each one of these letters you shift over 3 times, right? So anybody might know, hey, I know that a Caesar cipher is where you shift the letters in the alphabet. That's common knowledge. But what would not be known and what's secret is your key. They don't know whether it's 3, whether it's 10, whether it's 20. And so when you combine this key with the cipher, with the plain text, you can encrypt it. And then this is what you would get. This would be the result. And then to decrypt, you would need all that information as well, but you'd be shifting in the other direction, right? So hopefully this kind of helps solidify those concepts of ciphertext, key, and a cipher. And then encryption and decryption. So make sure you read through all that, and then they talk a little bit more about it here, and they talk about how really nowadays it's not much of a cipher, because with the alphabet we know there's only 25 possible keys because there's 26 letters, but if you shifted 26 times you would end up in the same place. So there's 25 possible keys, and that's really easy for us to go through, and they give that example here. So here is the ciphertext, right? So we can't read that, and you can just go through and try each one. Here's key 1, here's key 2, 3, 4, 5, and then if you get to key 5, it says this is Alpha Bravo contacting Tango Hotel Mike, right? So yeah, like this doesn't really work anymore, but it's a good example. And today we have very advanced mathematics and crazy smart mathematicians, and they create ciphers similar to this, but there's so many possibilities and so many potential outcomes that there's no way that anyone could just guess the key and then decrypt the information. Now over time there have been algorithms and ciphers that we used because they were secure for a while, but eventually a really smart guy who's good at math comes along and they figure out a way to decrypt it without the key. So anyways, I digress. So make sure you read through all that, and then there's a bunch of other cool historical ciphers. You can learn about them, just Google them real quick, and yeah, they're pretty cool. There was that movie Enigma, if you saw that. So that was all about ciphers, or one cipher in particular. Now down to the questions. Knowing that this, I'm going to copy this. So knowing that this string was encrypted using a Caesar cipher, what is the original plain text? So let's do this. So I'm just going to do a quick Google search, and then we'll do a Caesar cipher decrypt, and then, oh, look at that. Oh wait, nah, this is AI just telling us how to do it. Are they not going to just give me the answer, bro? Come on. Encode and decode online. Plain text. Okay, let me see here. So I'm going to take this, plug that into the plain text, and then let's see. So ciphertext, I'm just going to click through all of these until something makes sense. Wait, was that? Nope. Oh, here we go. So the answer to that is I can encrypt. And now that was 37. So if I go back to 0, We'll see which one it actually is. Oh, here we go. So that's being shifted 11 times. I think this website started me out on a different number and maybe I skipped it once, who knows. But yeah, so this is going to be the plain text. Or, well, this was the plain text that we got, but we decrypted it. Oh, I wasn't even using the decode. What happens if I do this? Will it just decode it for me? I don't know. I'm gonna stop screwing around because we already figured it out. So it's okay, never mind. I can encrypt. Okay, cool. So there's a bunch of different websites like this you can use. Just Google it and try and find one. And some of them will do it automatically for you. Others you might have to click through. But again, there's only like 26 possible outcomes, so, or 25, so you're good. So I can encrypt is the answer to that, and with that we are done with task number 4. Now it's on to task number 5, types of encryption, and this is really important, just because this is how our world kind of works today, and the concepts here are applicable for the most part to pretty much all ciphers that we're currently using on the internet right now and stuff like that. So we have symmetric encryption. So what that means is that we have this shared key. And so one key, right, we use the same key to encrypt and decrypt the data. So a lot like the Caesar cipher, right, that key is the number of shifts. So you have to know that number to both encrypt and decrypt, okay? So what you would do is you would encrypt using that shared secret key that Alice and Bob both have, and then she sends the ciphertext over email, let's say, and even if somebody intercepts it, they can't read it because they don't have the secret key. But Bob, he does have the secret key, so he gets the email, he decrypts it using his secret key or the shared secret key, and then Bob is able to read the email. Now, if you're thinking about this, you might already realize that there's kind of a problem. And the problem is how did Alice and Bob both get the shared secret key, right? Because Alice can't just email Bob the secret key, or else someone could get into Bob's email and they'd have the secret key and the encrypted email that Alice sent after the fact, right? So this type of cryptography, again, it works great if you have a secure channel and you know it's secure through which you can share that secret key. If you can't, like, if someone's on the other end of the world and you're not going to meet them in person, or you don't know of any way to get them a shared secret key through a channel that is totally secure, then this would be difficult to do. So read through all this. They explain it at the top, and then down here at the bottom they explain it more, where and they basically say what I said, which is you can't email them the password to unlock something. Right here it explains that. So that's why this form of encryption, it's still used, but it's not used when you're trying to send a message. We have a different form of encryption called asymmetric encryption, and we'll talk about that in a sec. So make sure you read through all this, make sure you understand the example, and the key part here is one key. One key both encrypts and decrypts. And then they give us some examples of symmetric encryption. So we have DES, which was adopted in 1977, and eventually it was broken. And so what happened was we were able to break that encryption in less than 24 hours. So then they shifted to this 3DES thing, but again, that didn't last very long, and eventually they went to AES, which was adopted as the standard in 2001. Okay? And AES stands for, what does that stand for again? Advanced Encryption Standard. And so you have keys that are different sizes, 128, 192, or 256 bits. So read through that. These two are kind of outdated, or not kind of, they are outdated. We don't use them anymore. We really use AES. So that's what we're using today for symmetric encryption. And then the next thing we're going to talk about is asymmetric encryption. And this is a pretty clever idea. I don't know exactly who came up with it, but they must have been a smart dude, because it solves our big problem with symmetric encryption. So asymmetric encryption, the way that it works is both parties, so Alice and Bob, both have two keys. One is called a public key, and everybody knows what the public key is. That's fine. And one is called the private key. So Bob has a public and a private key, and Alice has a public and a private key. So the way that asymmetric encryption works is one's public key is used to encrypt data, and then a separate, different private key is used to decrypt it. And this works out really well because what Bob can do, and I'm going to go back further in time before this even starts, right? So, or no, I'll just go through the diagram. So Alice, she wants to send a message to Bob. So she types up her message. And then before she encrypts it, Bob has already previously shared his public key with Alice. So Bob said, here you go, here's my public key. So Alice uses that to encrypt her message. Now she has ciphertext, but she can't decrypt it with Bob's public key, right? Because there's separate keys. There's one for encryption, one for decryption. So if somebody intercepted this message and had Bob's public key, it wouldn't help them at all. They still wouldn't be able to decrypt it, right? And so that kind of solves our problem of having a shared key. Now, once Bob receives this message that has been encrypted with his public key, he has his own private key, and he can use that to decrypt it. And Bob doesn't give anybody this private key. Only Bob has it. And then Alice has the same thing. So Alice has her own public and private key. So if Bob wanted to turn around and respond to Alice, he would get her public key, encrypt a message, send it to her, and then she has her own private key that she has never shared with anybody, not even Bob, and she'll use that private key to decrypt the message that Bob encrypted with her public key. So that second half, again, it gets a little wordy. I understand. You might have to look at the graph for a minute just to really understand this, but it makes a lot of sense once it kind of clicks and you realize how great of an idea this is. So make sure you read through everything. Pay attention to this diagram, especially the first half where I talked about Alice and all that. And hopefully you can understand why you would want two keys. So make sure you read through that. And then down here again, it gives us some examples of two-key encryption, or asymmetric encryption is what we refer to it as. And yeah, so make sure you read through everything, and then summary of new terms. Okay, so Alice and Bob are fictional characters. I think we know that. Also, by the way, just in case you were wondering, this is like true across multiple types of encryption. I don't know why and who decided it was Alice and Bob, but if you just Google asymmetric encryption, you'll get this same example. So it's not only on TryHackMe, it's literally everywhere. And then we also learned about, obviously, symmetric encryption and asymmetric encryption. So now down to the questions. Should you trust DES? Nay, you should not. That has been deprecated, it's old, and it was encrypted. When was the AES adopted as an encryption standard? Let's see here. AES was adopted in 2001. Sweet. So with that, we are now done with task number 5, types of encryption. Again, if you're kind of lost at any point with this whole encryption thing, even as you move on to the next rooms, this is a good task to come back to get that refresher about symmetric and asymmetric encryption. So keep that in mind. And now it's on to task number 6, basic math. So this is really good to know. It's a bit more complex. If you don't fully understand it, don't stress out too much, because you'll get it eventually, and it's not like something, depending on what you do for work, you can work in cybersecurity and you might not do this a ton or ever, but it's still good to know. So what we're going to talk about is we're going to talk about 2 different operations that are used in algorithms, and they're used for different reasons. I won't get into that. That's a little bit beyond this. So, but what they're called is the XOR operator, or that's what people call it. So it's the XOR operation, and then the modulo operation. And so this has to do with binary, right? Both, not the modulo, but this XOR operator is a binary operation. And what it does is it takes 2 bits and compares them, and if they are the same, it gives you 0. If they are different, it gives you 1. Right? So we can see that here. Anytime that 2 bits are different, it's going to give us 1. Anytime that they're the same, it'll give us 0. So read through all this. Try to understand it as best you can. It gets a little complex down here, especially if you don't have a big math background, or, if it's been a long time since you've done like high school algebra or something. But I'll kind of read through this and explain some of it. So that's all this is. When you really think about it, it's pretty straightforward. And they give us an example here. I think they do. We're going to XOR these 2 numbers. So it's real easy. So we compare the first number, 1 and 1. Those are the same. So that's going to give us 0. So our first number is 0. And then 0 and 1, those are different. So that's going to give us 1. Oh, here's the answer right here. So the first one is going to be 0. Then we get 1 because the next ones were different. Then let's go to the third number. 1 and 0, those are also different. So that'll be 1. And then 0 and 0, those are the same. So that'll be 0. Okay? So it's not that complicated. Down here, and understanding why it's useful in cryptography, and then understanding how cryptographers use it, that's where it gets a bit more complicated. But the point that they're trying to make here is that XOR is commutative. And what that means, well, there's 2 things. It's commutative, like they say right there, and it's associative. So commutative just means that the order of A and B doesn't matter. So the order of the individual parts doesn't matter. And then when it says it's also associative, what that means is if you group them off, so see how we have this A and B group, and then we're going to XOR that with C, and vice versa. So the group order doesn't, or the grouping, I should say, not the group order, but the grouping itself doesn't matter either. And those are 2 very important traits. So the individual order of, in this case, these letters doesn't matter. So, or these values. So the individual order of the values doesn't matter. And if you group the values, the order of that also doesn't matter. Or the grouping doesn't matter. So you can make different types of groups and it won't make a bit of difference. Okay? So that's what commutative and associative is. And they can use that to make symmetric encryption. And then they explain that using the values P, which stands for plain text, K, which stands for key, and that would be equal to the ciphertext. So when you XOR that with, so take the plain text, you XOR that with your key, and that'll give you the ciphertext, right? And then you can undo it. And if you really want to dig in, you can look through all this, and this will explain exactly how, if you only know the ciphertext and the key, you can still recover P. And they just do that through showing you these different math equations, right? So in this case, you know the ciphertext, you know the key, and you know that that is equal to the plain text XOR K, and then XOR K. And anyways, so I'm not going to get too into this because you could spend quite a bit of time looking at it and trying to understand it. But just know that due to these traits, how it's associative and commutative, you're able to do this, right? So you can take plain text, you can use XOR to turn it with a key to make it ciphertext, and then you can undo that using the same key. And because we're using the same key, that would be symmetric encryption, right? So now we'll jump down to the modulo. That's what I call it. People might pronounce that differently. I don't know. But anyways, so what this does is this divides the number and then results in the remainder. And that probably didn't sound great. So just read through this, and then the examples really help. So this is the symbol for the modulo operator. And what this does is it says 25 modulo, or modulus, I think is also something that people say. I don't know. Anyway, so it's 25 modulo 5. So what does that do? So when we do this, we're saying 25 divided by 5, right? But the result is not the result of division. The result is the remainder after the division. So 25 is the same as 5 times 5. So 5 goes into 25 5 times, leaving 0 left over. So that's why the answer to 25 modulo 5 is 0. And then you can look at this example, 23 divided by 6. So 23 divided by 6 is 3, but it has 5 left over. So that's why the result of this is going to be 5, and so on. So read through that, and hopefully you can kind of understand, how modulo works. It should be pretty straightforward once you read through these examples. And what's important, the reason why modulo is used in encryption is because it is not reversible. Okay? So, for example, 25 divided by 5 equals 0. So if we were given some number, pick a number, like X, right? So just a variable there. So if we only knew that a number was modulo 5 equals 0, we could not figure out 25 because there are an infinite number of possibilities there. And they explain that right here. They give you this little equation, X modulo 5 equals 4. And if you really think about it, you cannot figure out X because there are so many numbers that would satisfy this equation, as it says. So that's important. And then you also should note that the modulo operation always returns a non-negative, so it's always going to be a positive number, but it does have to be less than the divisor, right? So they give you an example. So for any integer a and positive integer n, the result will be the result of a modulo n will always be in the range of 0 to n minus 1. Okay, so basically the result of this has to be less than 25. But again, if we're not given 25, if we're just given this, we can't figure out this first number. So that's why it's kind of used, and that's why it's a useful operation, is because it's not reversible. So you can, if you think about it, you may be able to kind of put it together and understand, wow, that would be really useful in asymmetric encryption, where you have one key encrypting, one key decrypting, right? Because certain things aren't really reversible there. So yeah, anyways, read through that, and then hopefully you kind of understand both of these operations. And then we'll jump down to the questions. What is 1001 XOR 1010? So that would be 1 and 1 are the same, so that gives us 0. 0 and 0 are the same, so that gives us 0. 1 and 0 are different, that gives us 1. 1 and 0 are different, that gives us 1. So I just compared each byte, and that's all you have to do for that. And then this, honestly, this is such a big number. You could plug it into a calculator, but I'm just going to Google it real quick. Should just give me a result. There we go. So this is the remainder. If we were to do that operation, this is what we get as a remainder. And then 60 modulo 12. 12 goes into 60 in even amount, so there would be no remainder, I believe. So yep, there you go. So mark all of those, and with that, we are done with task number 6. Now it's on to task number 7, the summary. So yeah, basically, you learned a little bit about encryption. Again, if some of this math stuff felt like a little bit of a stretch for you, don't worry too much about it. I would argue to say the most useful part of this room was definitely these diagrams and the explanation of symmetric and asymmetric encryption. So make sure you know those pretty well, especially before you move on to the next room, which will be public key cryptography basics. So make sure you check that out. I hope you guys found the video helpful. If you did, give it a like and subscribe. That helps me out a ton. And with that, we have finished all the tasks, and we have finished the cryptography basics room from TryHackMe.